Now this first part of 2.7, if you're looking at your paper versus what's on my screen, you'll see it's different, right? I've already done the problem for you on your paper, but I want to do it live here so you can watch me actually do the problem, but you're going to be eyes on the screen, not on your paper. Yes, I'm color coding it. I will give you a second to catch up in the color code if you want, but just watch because I need you to hear what's happening. It was not clear in first period or honestly last class how to do function composition. The first concept in 2.7 is the idea of verifying function inverses. So what we're working with today is not inverse operations, but inverse functions and some of the properties of inverse functions. We're going to need to find them, we're going to need to verify them, and then look on a graph. But first, let's work on verifying. The rules are, and again, I just want you to listening. I will give you time to write anything down in just a second. A function has an inverse if two functions can be composed with each other, and either direction that you compose them, you get out x. Meaning, if I take f and I plug what I'm claiming to be its inverse, f inverse, inside of it, simplify, it should be x. If I take f inverse and I plug in the original function f of x, compose it, simplify it, I should get out x. So what you'll be doing in problems when it asks you to verify or show that each function is an inverse is you will take the two functions that we are claiming are inverses and we will compose them both directions, with g on the inside, then with f on the inside. If we get out x both times, you would confidently say, yes, these are inverses. So if I was solving this first problem, I would do, whoa, why is that so large? I would do f of g of x. So I have f on the outside, g on the inside. So f on the outside, the function g on the inside. Is everyone following so far? Now I'm going to rewrite down the pink function f, 3, and I'm going to write x for a second, plus 2. In the place of x, replacing it, not smushed next to it, but replacing the x, I'm going to put x minus 2 over 3. I'm going to put that function in there. Now I just have to simplify. Hopefully your spidey senses are going off because you have a 3 on top and 3 on bottom. What's going to happen here? They cancel out. So I have these two numbers canceling out, and I'm left with x minus 2 plus 2. Ooh, minus 2 plus 2. What's going to happen there? Cancel out. What am I left with? We want that. We want it to be x. Now we need this to happen both directions, which means I'm not done with this problem. I'm going to start over, this time putting g on the outside and f on the inside. If I do this, putting g on the outside and f on the inside, I'm going to rewrite down the g function, which is x minus 2 over 3, but instead of x, what am I putting there? 3x plus 2, completely replacing the x. Take the x out, put this in. We have minus 2 and plus 2 in the top. What's happening there? Oh, that's nice. Then we're left with 3x over 3. What's happening there? The 3's will cancel out. What am I left with? That's what I want. If, when you do this both directions, you get x both times, that's when you're showing that these functions are inverses. So we would say confidently, yes, these are inverses. If you were solving this, and let's say this one you got 5x, and on this one you got 7x, are those inverses? No, they should give you exactly what out? X. I will give you a second to catch up because I just highlighted a whole bunch of things. If you like the color code, catch up. If you don't, just hang on while everybody catches up. So again, that's verifying. You will know you'll be doing this if the question uses the word verifying or show that each is the inverse. That's your indicator that you're going to have to compose them both directions to make sure you get out x. But what happens if we're not given an inverse and we're asked to actually find it? Here's the steps we're going to take. Number 1, it's a two-parter for number 1. You're going to replace the f of x with just a letter y. And then main idea here, we are going to switch the x's and y's. Just boop, boop, replace them. When we switch the x's and y's, after that, you're going to resolve the equation for y. Resolve is not a real thing. It's just solving the equation for y. But you're going to rearrange it so that y is by itself. This may require you to do linear things, quadratic things, cubic things, maybe rational things, but we're resolving so that y is by itself. then the finished step is to clean it up and replace the y back with the symbol for the inverse, which is f inverse of x. It's f with an exponent of -1, but it's not an exponent. It's a notation saying these are inverses. Shall we see an example together? We have f of x equal to 7x minus 5, and we are finding the inverse. Number 1, we replace f of x with y. Once it's replaced with y, we just swap the x's and y's in their positioning. Literally just replacing y with x and x with y. Did I change anything else about this question? Did I change just the x's and y's? Yes, change nothing about anything else on this equation. My job now is to solve this equation so that this y is by itself. If we're trying to get that y by itself, what would I have to do first on both sides? Add 5. So this is x plus 5 equal to 7y. Y is not by itself yet. So what do I do? Divide by 7. So I'm going to divide both sides by 7 so that y is by itself. If you can actually divide the numbers by 7, you would. Neither of these numbers, 1 or 5, can be divisible by 7. So when we're cleaning this up, we would write this as f inverse of x is equal to 1 over 7x plus 5 over 7. Now your homework today is going to ask you to write these inverses and then make sure you talk about the domain. It's going to be the domain in inequality notation. What kind of function did I create here? Linear. It's a linear function with a slope of 1 over 7 and a y-intercept of 5 over 7. Do linear functions have any domain restrictions? No, so you'd select the example that says that you can use all x's from -infinity to infinity, or all real numbers. Did I lose anybody on any step here? Change f of x to y, switch the x and y, solve for y, make it pretty. Can we try another one? Okay, this time we're finding the inverse of g of x. I'm going to first change the g of x to y so that I have x's and y's, so that it makes a lot of sense to me when I say switch the x and y. Literally replace y with x and x with y. Again, did any other part of this equation change except for x's and y's? Notice that the cube didn't move. It's now cubing the y. Cool, we swapped the x's and y's. Our job is to solve for y. So how do I get this y by itself? -1 on both sides. Okay, now the y cubed is isolated. How do you get rid of a cube? Cube root. Do you need the plus or minus on a cube root? It's an odd root? No. What are the only things that you need plus or minus in front of? Even roots, square roots. So you just get to cube root both sides, which would get the y by itself. Cube root of x minus 1. And if we were writing this fancy notation, we would say g inverse of x is the odd third root, of x minus 1. For odd roots, are there any restrictions on the domain? No, so you'd select the option that says you can use all x's. Square roots have restrictions on their domain, but cube roots do not. Questions about either of these two? So again, change it to y, switch x and y, solve. That's exactly what we're going to do on this last one, which is kind of crazy, and I've already done it for you. But if you notice, the first thing we did here where this blank is we switched the x and the y. What? We switched the f of x for y, sorry. And the problem is that this rational function is a little bit more complicated in the solve for y portion. So we switch f of x to y. And when we swap the x and the y, what do you notice about the y's? Is there one y? There's two y's. Makes this a little bit more complex because when we were highlighting the y to solve, it was very easy. We just did inverse operations. The inverse operations to solve this are a little bit more complicated. Because there are two y's, my first goal to solve for y is to somehow combine them together into one y so that I can isolate one y instead of two y's. The first thing you're going to do on both sides is you are going to multiply by the denominator, because we want to get that y minus 3 out of the denominator. When you multiply by y minus 3 on both sides, the denominator goes away, and now there's a y minus 3 on the other side. Do we see how that happened? What did I do to go from this step to this step? We distribute the x, because it says x times that parentheses, so I'm going to go ahead and distribute the x. Okay, so now I have this function with 4 terms. 1, 2, 3, 4. How many of those terms have y's in them? 2. How many of them do not have y's? So we want to organize this to where all the stuff with y's is on the left side and all the stuff without y's is on the right side. So this next step, I'm just going to call it move. You're moving the 3x to the other side, and you're moving this y to the other side, so that all of the y's are on one side and all of the x's are on the other. Because remember, our goal is to somehow combine these y's together. Are xy and negative y like terms? No, so we can't combine them like adding and subtracting. But in these two terms, what do these two terms have in common? Y. If it's in common between two terms, what can we do with that in common term? Take it out. This is called factoring. So the next step is to factor out the y. You're taking the y out of both terms. If you take y out of this term, all you're left with is x. And if you take y out of this term, all you're left with is 1. Okay. Now, how many y's are left in this equation? 1. Hooray! We've got 1 y left, which means we can isolate that 1 y. How did we do that to go from here to here? How did I get this y by itself? Divide by that stuff in parentheses. Now, when you do this division, 98% of the time, you won't actually have to do dividing. You're just going to stick it down there in the denominator. Once y is isolated, you're done. All you have to do after that is make it fancy and make it f inverse. You also created a problem, right? You made a denominator. What can that denominator not be equal to? Positive 1. So if you were doing this one, you'd have to select the option that says x cannot be equal to some number and put the number 1 there. We're always qualifying these things with domain restrictions. So that part does not go away from 2.6. Take a second, because that was a lot. Let's look back from top to bottom of this problem, and if there's a moment you have questions on, let's discuss. The back of your notes is going to start talking about these ideas on a graph, because inverse functions on a graph have very particular characteristics. In fact, there is a test that we can employ to decide if functions have an inverse. That is called the horizontal line test. We're familiar with the vertical line test, yes? The vertical line test tells us if a graph is a function. The horizontal line test tells us if the graph has an inverse that is a function. Has an inverse that is a function. This is our test for unique input and output values. Unique inputs mapping to unique outputs. So let's back up a second. Here are 4 graphs. Before we do the HLT, let's do the VLT. Would this one pass the vertical line test? So it is a function. Would this one pass the vertical line test? So this graph is a function. How about this one? So this graph is a function, and then yes, so all of these graphs are functions. They're relations that are functions. They pass the vertical line test. The question now is, do these functions have inverses that are functions? Does this graph pass the horizontal line test? Yes. So we would say, yes, this graph has an inverse function. It has a function that is it has an inverse that is a function. It is invertible. What about the second graph? Does that pass the horizontal line test? No. So this function does not have an inverse function. It is a function, but its inverse is not a function. How about the letter C? Does that pass the horizontal line test? Big no. Look at that, 3 times. So that one also, that function, does not have an inverse function. It is not invertible. It does not have unique input and unique output values. But what about this last one? That one passes the horizontal line test, so what does it tell us? It tells us that yes, this function has an inverse that is a function. It passes a horizontal line test. Now, we've introduced the vertical line test in 2.1 and now the horizontal line test here in 2.7. And if we put those two concepts together, we have a new vocabulary word called a one-to-one function. A one-to-one function is a function that passes both the vertical and the horizontal line test. So we're going to be doing vertical lines as well as horizontal lines to test a function or test a relation to see if it is one-to-one. All functions that have inverse functions are one-to-one, and all one-to-one functions have inverses that are functions. So we would, if it asks you, is this function one-to-one? You do the vertical line test and horizontal line test. The answer has to be yes, it passes both, and then the function is one-to-one. It's unique input values and unique output values. But once we know that a function has an inverse that is a function, we're going to be able to graph those inverses on the same coordinate grid. So we're going to be graphing an original function f and its inverse at the same time. But don't fret. Earlier, in that step 1, when we were solving for an inverse, what did we do with the x's and y's? Switch them. So all we're going to have to do with each coordinate point, which is always x and y, is literally just switch them, and it will create our inverse function. So if you notice on this graph, the graph of f has a comma b as a coordinate point. So without thinking too hard, I know I can plot b comma a, just switch the x and y, and that point belongs to my inverse function. There's a visual help here too, that when you're done, f and f inverse should be reflections of each other across a diagonal line with a slope of 1 and a y-intercept of 0. The diagonal line, y equal to x, it should flip one graph to the other. So if we were to fold these notes right here on this line, wouldn't this curve land right on this curve? That means that we have visually seen that they are inverses of each other. Okay, so we do just switch the x's and y's, and then we double check that it actually flips over the line. One more note for us today, because we said we are switching the x's and y's, and x's are domains, and y's create the range, we also know that we can switch the domain and the range to create the domain and range of f inverse. So the domain of f is equal to the range of the inverse, and the range of f becomes the domain of the inverse. Switch the x's and y's, you switch the domains and ranges. In example 5, it says to use the graph of f to draw the graph of its inverse function. First things first, does this pass the vertical line test? It is a function. Does it pass the horizontal line test? Its inverse is a function. Is this a one-to-one function? Yes, because the answer to vertical and horizontal was both yes. So if we're plotting the points, all we're going to do is take these coordinates and do what with the x and y? Switch them. Yes, flip, but let's use the word switch. So if we do that, this first coordinate point, -3, -2, becomes the coordinate point what? -2, -3. We can plot that point. The coordinate point -1, 0 becomes what? 0, -1. Thank you. And that last coordinate point, 4, 2 becomes what? 2, 4. I'm gonna try drawing that line again because that's just embarrassing. I literally have my ID on the screen.
Like the notes
I do, but I was trying to draw it normal. Here we go. Is that better? Oh! I am having a day, guys. Is that better? Bye, Kevin. Have a good day. Okay, so here's the last little check I want us to make. And this is a little bit harder to do maybe like by hand because you don't have a straight line tool. I was actually going to use my straight line tool for this. If we were to draw a straight line from corner to corner here, oh my gosh. Listen. Okay, from corner to corner. Do you see that the original graph, F, and our F inverse flip over that line? These are inverses. We switch the x and y. It's a reflection over the line y equal to x. The domain becomes the range becomes the domain. Oh, okay, it's stuck. Now the last question here on our notes says that we're going to find the inverse of f of x equal to x squared minus 1 if x is greater than or equal to 0, and then graph the two things in the same coordinate grid. I've already graphed the quadratic for you that we're starting with. This is a quadratic with a vertical translation down 1. So here's my quadratic, and it starts at -1 because I pulled it down 1. And we're going to graph the other inverse in the same coordinate plane. So let's first just find the inverse of this function. I would switch the f of x to make it a y. Then I would switch the x and y themselves. This would be x equal to y squared minus 1. I would solve for the new y so that I can get y by itself. What would I do first for that? Plus 1 equal to y squared. And then do what? Square root. Ooh, square roots. What do we have to put in front of square roots? Plus and minus. Okay, cool. So plus and minus square root of x plus 1 equal to y. Now, we have a question here that says, when we're starting this anyways, find the inverse of f of x, x squared minus 1, if x is greater than or equal to 0. Since this says x is greater than or equal to 0, do we think I should use the positive or the negative sign in front of that square root?
No, positive.
The positive. If that had switched the other direction, you would keep the negative sign, which means the actual inverse function here, f inverse of x, is just the positive x plus 1. Square root of x plus 1. Square roots. What kind of numbers can I not plug into square roots? Negative. Somebody whispered it. Negative numbers. So what we'd have to do is say x plus 1 has to be greater than or equal to 0, which means x is greater than or equal to -1. From -1 to infinity. So if this was a problem on your homework, you'd select the option that had a domain restriction that x is greater than or equal to -1. But what we want to do is we want to graph this function. Say again?
Never mind.
Well, we are going to actually use the graph to help us. This graph is the graph of the quadratic x squared minus 1. But we're only using the part of it where x is greater than 1. Does that mean we're using the left side or the right side? The right side. So I'm going to scratch this one out. Don't aggressively scratch it out because you're going to need some coordinates in here. But if I get rid of this side, I'm only working with the quadratic that's on the right side. We had to throw away the left side. This quadratic on the right side, where it's increasing, I see 3 pretty good coordinate points here, here, and here that I can switch the x and y for. We're going to plot them and connect the dots. This coordinate is 0, -1, which means I should plot what? If this is 0, -1. -1, 0. This is why I told you not to scratch it out aggressively, because we actually need this coordinate point right here, which is kind of annoying. I'm so sorry. For the second coordinate point, that is 1, 0. So what should I plot? 0, 1. The last coordinate point is 2, 3. So what should I plot? 3, 2. At this point, we can play connect the dots. And we'd see that that does kind of look like the parent function for a square root. It's just been translated which direction? Left 1, which makes sense because we put +1 on the inside. Whoa. What? Let's do one more quick check though, and I'm going to grab my line tool. And we're going to do the line y equal to x, which is not corner to corner on this graph. But if you go from origin to corner, because I cut off part of this graph, do you see that this would be, and I'm going to continue it this direction, this would be a reflection of the right side of the quadratic to the square root function.